Hello everyone. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today I am going to discuss about collision, the types of collisions, that is elastic and inelastic collisions. So first of all, what is the importance of collision matter in engineering, especially that is computer science? So these collision matters are used in data science, that data science and simulations, robotics, artificial intelligence, game development, and graphics. These are also used in cyber physical systems, virtual reality. So data science and simulation, it is using in modeling and analysis in particle simulations and network traffics. So robotics and artificial intelligence, the collision matters are used in safe interaction and efficient energy transfer in robots. So in game design or game development and graphics related also, the collision matter is used, that is realistic animations and object behavior in gaming. So cyber physical systems, in it the safety design and crash simulations for autonomous vehicles are used, the collision matters. In virtual reality also, the collision matter is used, that is immersive experiences through realistic collision responses. So first of all, what is the collision? What are the types of collisions we try to understand? What is the collision? The interaction between two or more, the interaction between two or more bodies, which leads to change in their momenta, is called collision. So during the collision, the colliding bodies may or may not come into direct contact. During the collision between two spherical or metallic spheres, it contact directly. But between alpha particle and nucleus, there is no direct contact between nucleus and alpha particle. So try to see here. So collision. You see here definition. The interaction between two or more bodies which leads to change in their momenta is called collision. So, linear momentum is equal to the product of mass into velocity. So, if changing the momentum, if the two or more bodies collide with each other, the momenta can be changed. So, the interaction between two or more bodies which leads to change in their momenta is called collision. So during the collision, you try to understand colliding bodies may or may not come into direct contact. For example, during the collision between two metal spheres, they come into direct contact. This is direct contact. This is first one. Example number one. Whereas during the collision between alpha particle and atomic nucleus, do not come into direct contact. You try to see here. During the collision, the colliding bodies may or may not come into direct contact. So that is the example. Between two metal spheres, there is no direct contact. Between alpha particle and atomic nucleus, they do not come into direct contact. Collision may take place in one dimensional or two dimensional or three dimensional. So the collision can move along x direction or xy, that is plane. For space three dimensional xyz, also we can observe the collision may take place in one dimensional or two dimensional or three dimensional. Types of collisions. Collisions are two types. They are number one, elastic collision, and number two, inelastic collision. So, what is elastic collision and what is inelastic collision? We try to understand here. So, what is elastic collision? The collision in which both momentum and kinetic energy are conserved. That is called elastic collision. Elastic collision. So, for example, in elastic collision, the collision in which only momentum is conserved but not kinetic energy is called inelastic collision. Inelastic collision. So, coming to elastic collision and inelastic collision. So, we can also here distinguish between elastic and inelastic collision. So, elastic collision definition, try to understand here the collision in which both momentum and kinetic energy is conserved. What is that? In this collision, the total momentum m1u1 plus m2u2 is equal to m1v1 plus m2v2. This is the before collision m1u1 plus m2u2, after collision m1v1 plus m2v2. In this collision, total momentum before collision is equal to total momentum after collision. So kinetic energy also in this collision, the total kinetic energy before collision, this is the before, this is after. So before collision, of m1 u1 square plus of m2 u2 square is equal to after collision half m1 v1 square plus half m2 v2 square. The temperature of the system remains constant because it is a elastic collision. The bodies regain their original shapes after the collision. For example, collision between alpha particle and a nucleus. And another example, collision between fundamental particles and nucleus. Coming to inelastic collision. So, definition, the collision in which only momentum is conserved but not kinetic energy is called inelastic collision. Inelastic collision. So, in this inelastic collision, the momentum is conserved. In this collision, total momentum before collision, this is before collision, is equal to after collision. So in this collision, total momentum before collision is equal to the total momentum after collision. So next one, in this collision, the total kinetic energy before collision is not equal to the total kinetic energy after collision. So the temperature of the system changes because they directly collide with each other. The bodies cannot regain their original shapes after collision. After collision, because they are directly collide with each other, so they cannot get the original shape after collision. What are the examples? Collision between two vehicles. Number two, collision between cricket bat and ball. So try to understand the distinguish between elastic and inelastic. So both sides you try to understand here. So definition: the collision in which both momentum and kinetic energy are conserved. But inelastic, the collision in which only momentum is conserved but not kinetic energy. That is called inelastic collision. So in both cases, elastic and inelastic, the momentum is conserved. Both are same. In this collision, the total momentum before collision is equal to after collision. That is m1u1 plus m2u2 before collision, that is equal to m1v1 plus m2v2, that is after collision. So here you see this is in elastic, the total kinetic energy before collision is equal to total kinetic energy after collision. But in inelastic collision is not equal to. In this collision, total kinetic energy before collision is not equal to total kinetic energy after collision. So in a elastic collision, temperature of the system remains constant, but in inelastic it is changing. That is, temperature of the system changes. The bodies regain their original shapes after collision. But in inelastic collision, the bodies cannot regain their original shapes after the collision because they directly collide with each other. In elastic collision, the bodies regain their original shapes after collision because they are not directly collide with each other. So examples of elastic, you can see collision between alpha particle and nucleus. So second example, collision between fundamental particles, electron, proton, neutron, something. So fundamental particles, alpha particle, beta particle, so something. So collision between fundamental particles and nucleus is the example of elastic collision. Inelastic collisions, collision between two vehicles. Second example, collision between a cricket bat and ball. So coming to one-dimensional elastic collision. After collision, we need to calculate the final velocities v1 and v2. So try to understand here one-dimensional elastic collision. So let two bodies of masses, this is m1, this is m2, travel along a straight line in the same direction with velocities u1, u2 respectively. Let u1 should be greater than u2. Then collision takes place between them after some time. After collision, the two bodies travel along the same straight line in the same direction with velocities v1 and v2 respectively. So what I am saying, let us take two bodies of masses m1 and m2 travel along a straight line in the same direction with velocities u1 and u2 respectively. Let u1 should be greater than u1 should be greater than u2. Then collision takes place between them after some time. After collision, the two bodies travel along same straight line in the same direction with velocities v1 and v2. So according to law of conservation of linear momentum, we know very well m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So I want to take this is left side here. So M1 U1 minus M1 V1 is equal to M2 V2 right side as it is. I want to take this is minus M2 U2. So taking the common M1, so this is U1 minus U1 minus V1, M2 common, that is V2 minus U2. So try to see here. So what I'm saying here, according to law of conservation of linear momentum, M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Let this is the equation number one. So the equation one we can write M1 U1 minus M1 V1 is equal to M2 V2 minus M2 U2. So taking the common here M1, I am taking here common. So M1 into U1 minus V1 is equal to M2 common V2 minus U2. That is equation number 2. So second point, according to conservation of kinetic energy. So kinetic energy before collision half m1 u1 square plus half m2 u2 square is equal to after collision kinetic energy half m1 v1 square plus half m2 v2 square. From these two equations we can take the common half, so half gets cancelled. Remaining we can write m1 u1 square plus m2 u2 square is equal to m1 v1 square plus m2 v2 square. Same, this is same. So in this also, I want to take this is m1 u1 square. I am taking this part left side minus m1 v1 square is equal to m2 v2 square minus m2 u2 square. Taking the common m1, so this is u1 square minus v1 square. Taking common right side m2, so this is v2 square minus u2 square. That is equation number 3. You see here common m1 into u1 minus u1 square minus v1 square. That is equal to m2 into v2 square minus u2 square. So just to take equation 3 by equation 2. So you know very well, equation 3, this is the equation 3. This is m1 u1 square minus v1 square is equal to m2 into v2 square minus u2 square divided by equation number 2, that is m1 into u1 minus v1. Here also m2 into v2 minus u2. M1 gets cancelled. Here M2 gets cancelled. So u1 square minus v1 square. So a square minus b square formula. A plus b into a minus b. So I am taking here this u1 square minus v1 square, that is u1 plus v1 into u1 minus v1 divided by u1 minus v1 is equal to, so again that is a square minus b square formula, a plus b into a minus b, v2 minus u2, or v2 minus v2 plus u2 into v2 minus u2 all divided by v2 minus u2. So v2 minus u2, u1 minus v1 gets cancelled. So remaining, what is this? u1 plus v1 is equal to v2 plus u2. That is the formula. So now, hence, from this relation v1 is equal to v2 plus u2 minus u1. Let this is equation number 4. From this relation, V2 is equal to U1 plus V1 minus U2. That is equation number 4. So next, coming to this one, to find E1, you try to see here to find V1 from 1 and 5th we get. So this is the 5th V2. So M1 U1 plus M2 U2 is equal to M1 V1 plus M2 into U1 plus V1 minus U2. From this relation, just write as it is left side M1 U1 plus M2 U2 is equal to. So this is M1 V1 as it is right side plus M2 U1 plus M2 V1 minus M2 U2. So from this relation, we can take here, you see, M1 U1 as is M2 U2 plus M2 U2. This is 2 M2 U2 is equal to V1 into M1 plus M2 plus M2 U1. From this relation, just take a common V1 into M1 plus M2, that is equal to M1 minus M2 U1 plus 2 M2 U2. So what is this formula? V1 is equal to M1 minus M2 by M1 plus M2 into U1 plus 2M2 by M1 plus M2 U2. So to find V2 form from equation 1 and 4. Equation 1 and 4. 4 is the V1 is equal to V2 plus U2 minus U1. Just substitute that V1 value in M1 U1 plus M2 U2 is equal to M1. This is V2 U2 V2 plus U2 minus U1 plus M2 V2 plus M2 V2. This is M2 V2 as it is here. So M1 U1 plus M2 U2 is equal to M1 V1. This is M1 U2. What I am saying here, M1 U1 plus M2 U2 is equal to M1 V2 plus M1 U2 minus M1 V1 plus M2 V2 as it is. So we get 2M1 U1 plus M2 U2 minus M1 U2. That is equal to M1 V2 plus M2 V2. Just to take the common V2, finally V2 is equal to 2M1 by M1 plus M2 into U1 plus M2 minus M1 by M1 plus M2 into U2. So simply you can remember here V1 is equal to, this is U1 plus this is U2. So remember this denominator, both are same M1 plus M2. Here also M1 plus M2. For this V1, for this one, take the differences of masses M1 minus M2. Remaining, this is 2M2. Similarly, V2 is equal to take this is U1 plus take this is M2, same. So denominator is also same M1 plus M2. Here also M1 plus M2. For V2, at the place of V2, take the mass differences high value minus low value M2 minus M1. Remaining, this is 2M1. You observe this is 2M1. This is also 2M2. Just observe these two equations. We can easily remember. Coming to next, collision is the interaction between two or more bodies in which sudden changes of moment takes place. So, momentum, we know very well, P is equal to mass into velocity, always conserved in isolated collisions. So kinetic energy half mv square may or may not be conserved. Time of collision is very short, so external force negligible. Elastic collision. The elastic in which both kinetic energy and momentum are conserved is called an elastic collision. So elastic collision, we can see Newton's cradles. Try to see, these are the Newton Newton's cradles. Newton's cradle. You try to understand. The collision in which both kinetic energy and momentum are conserved is called an elastic collision. So, according to this Newton's cradle, we can observe the elastic collision. Conservation of kinetic energy also we can observe here. Half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So another example also, conservation of linear momentum in atomic particles. So collision between ivory balls. What is that ivory balls? You can see here tusks of elephants or a billiard or snooker ball, traditionally made from ivory in the past. So conservation of linear momentum, example, or elastic collision, example, collision between ivory balls or atomic particles. You try to observe here. You try to observe here. Elastic collision, the collision in which both kinetic energy and momentum are conserved is called an elastic collision that can be observed using the Newton's cradle. So here, that is the kinetic energy is conserved, that is half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. Conservation of linear momentum also we can observe using these two examples. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. So examples, collision between ivory balls, you try to understand they are colliding, or atomic particles. Atomic particles. So coming to examples of elastic collisions. So billiards and snookers. That is the best example of elastic collision. The balls collide almost elastically, transforming momentum and energy also. So, Newton's cradles, we observed in our previous slide, it demonstrates conservation of momentum and kinetic energy in a series of swinging balls. Molecular collisions, another example. Gas molecules in an ideal gas collide elastically. The molecules are collide with each other and helping explain the kinetic theory of gases. Depending on kinetic theory of gases, how the molecules are collide elastically, we can observe. Ball bounce. A super ball that is like rubber ball bounces back nearly to its original height. That is also elastic collision. Spacecraft related elastic like interactions with planetary bodies allow related gain velocities without fuel. So these are the examples of elastic collisions, billiard ball, snookers, Newton's cradles, molecular collisions, ball bounces, and so on. So coming to inelastic collision, the collision in which only the momentum is conserved is called inelastic collision. So conservation of linear momentum m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Collision between bullet and a wooden, or collision between two balls. You try to see collision between two vehicles. So in this inelastic collision, the momentum is conserved but not kinetic energy. But not kinetic energy. So completely inelastic, that is two vehicles collide with each other. The car is collide with the another heavy vehicle like lorry. So two balls are collide with each other. So what are the examples of inelastic collisions? So car crashes, clay balls, sports, etc. That is industrial parking also. So we need to learn any two or three examples of inelastic collisions. Car crashes, you know very well. Vehicles deform, losing kinetic energy as heat. So crumple zones protect passengers. Clay balls. Thrown clay balls stick, moving as one mass. This is perfectly inelastic. You try to understand using these two. Car crashes, the two cars are collide with each other. The vehicles deform and lose their kinetic energy. So the before kinetic energy of collision and after collision kinetic energy is not equal, but the momentum is conserved. Clay balls also, thrown clay balls stick moving as one mass. This is preferably inelastic. So bells deform on impact, losing kinetic energy, momentum is still conserved. In all the examples of this inelastic, the kinetic energy is not same before collision and after collision. But the momentum is conserved. Momentum is conserved. So summary, coming to the summary, types of collisions we discussed in this class, the types of collisions we discussed. Elastic collision, we discussed inelastic collision and their examples. Preferably in an inelastic collision, also we discussed. So key principles, law of conservation of momentum and law of conservation of kinetic energy also we studied in these collisions. So application part also we discussed vehicle crash analysis, particle physics experiments, gaming and animation physics also. It is very useful for this types of collisions and collision. Thank you so much. Thank you. Thank you very much.